April 2026. 4 astronauts are sealed inside a spacecraft called Orion. They are 150,000 miles from Earth and climbing. Then a warning light blinks on. Inside Mission Control in Houston, engineers see it. Not through a window, not through a camera. They see it through data. So here's the question I want to start with. How does a room full of engineers in Houston know what's happening inside a spacecraft 250,000 miles away? What are they actually seeing? And how is that information getting back to Earth at all? The answer is telemetry. And once you understand it, you'll never look at a rocket, a drone, or even your car the same way again. Telemetry. It's one of those words that sounds more technical than it is. Here's the plain English version. Telemetry is how a machine reports what's happening inside itself, usually while it's somewhere you can't get to, can't see, or wouldn't survive visiting. A spacecraft in deep space, a drone beyond visual range, a race car doing 200 miles an hour, a wind turbine on a mountain in a storm. You can't walk up and check it, so the machine tells you. And it does that through a 5-step chain: sensor, data, transmission, receiver, decision. 5 steps. And every modern machine that operates remotely follows some version of this chain. On Artemis II, NASA was running thousands of them, simultaneously, every second of the 9-day mission. Let's walk through each one. The chain starts with sensors. A sensor is just a device that measures something and turns it into a number. Temperature, pressure, voltage, heart rate, acceleration, radiation. If you can measure it, a sensor can report it. On Orion, there were thousands, and they fall into 3 basic categories. First, what the spacecraft knows about itself: engine temperatures, propellant levels, power consumption, system pressures. This is health monitoring, the spacecraft telling engineers whether everything is working as designed. And here's a real example from before Artemis II even launched. In February 2026, a sensor detected an interrupted helium flow in the upper stage of the rocket. Engineers saw the data, pulled the numbers, and rolled the entire rocket back to the vehicle assembly building, a 4-mile, 12-hour crawl on the crawler transporter, before they could even begin to fix it. That's a sensor doing its job. Before a single astronaut strapped in. Second, what the environment is doing to the spacecraft. Artemis II flew to lunar distance, well beyond Earth's magnetic field, which normally deflects radiation. Radiation sensors tracked crew exposure the entire mission. NASA even tested a shielding configuration using water stored in Orion as protective mass. The sensors told them whether it worked. Third, what the crew is doing. Biometric telemetry, heart rate, respiration, how the body handles returning to gravity after 9 days of weightlessness. On the final days of the mission, NASA ran medical assessments, orthostatic testing, monitoring the crew's physiological response. That data fed the medical team before splashdown. Thousands of sensors, 3 categories, all running continuously. But measuring something is only step 1. Once a sensor produces a measurement, that number has to get back to Earth. On the ground, that's straightforward. Wire it, Wi-Fi it, done. But how do you transmit data 250,000 miles through space? NASA's answer is the Deep Space Network. 3 ground stations. 3 locations around the world: California, Spain, and Australia. Why 3? Because Earth rotates. One station always needs to be facing the direction of the spacecraft. As Earth turns, the stations hand off coverage to each other, creating a nearly continuous link. Now, it's worth pausing for a moment on how the communication link itself works. Telemetry is a one-way link. Data flows down from the spacecraft to the ground. That's the return link. And it's a dedicated stream carrying health and status data, separate from everything else. During the launch and ascent phase, telemetry runs on high-rate dedicated S-band downlinks, received at tracking stations along the Eastern Range. This includes Tel-4 at Kennedy Space Center and JDMTA, the Jonathan Dickinson Missile Tracking Annex, in Jupiter, Florida. That's the world of launch telemetry. Separate, dedicated streams providing real-time health and status data from the moment the SLS core stage and boosters ignite. Once Orion separates from the rocket and leaves low Earth orbit, the architecture shifts to a modern digital network. Instead of the analog subcarriers of the past, voice, video, and telemetry move on to an IP-based digital S-band link managed by the Near Space Network and Deep Space Network. Using modern modulation techniques, these systems multiplex Capcom audio, critical mission telemetry, and standard definition video into a single encrypted digital stream. Later in the mission, Orion tested a breakthrough in high-speed data, the Orion Artemis II Optical Communication System, O2O. Using an infrared laser rather than radio waves, O2O demonstrated bandwidths up to 260 million bits per second, allowing for 4K ultra-high-definition video streaming. It's a glimpse of where deep space communications are heading, moving from the dial-up speeds of radio to the broadband capabilities of light. Now here's something most people don't think about. Radio signals travel at the speed of light. That sounds fast, and it is. But at lunar distance, those signals still take about 1 1/3 seconds each way. That means the data engineers see on their screens isn't happening right now. It's happening 1 1/3 seconds ago. At Mars, that delay becomes 20 minutes. Telemetry is always a history of what was happening, not what is happening. And for real-time decisions, that distinction matters. Okay, the data has traveled 150,000 miles. It's arrived at mission control. Now what? Let me take you back to that warning light from the beginning. On flight day 2, early in the mission, a fault indicator appeared in Orion's waste management system, the toilet. Now, the crew can't exactly pull over, and there's no technician they can call. But mission control saw it. Here's how. Step 1. A sensor detected the anomaly and generated a reading. Step 2. That data was encoded and packetized on board Orion. Step 3. Transmitted via radio link to the Deep Space Network, routed to Houston. Step 4. Engineers saw it on their consoles. Not a blinking light, actual parameter data. Step 5. They analyzed it, communicated a fix to the crew, and confirmed the system was restored via follow-up telemetry. Sensor, data, transmission, receiver, decision. Every step, 250,000 miles from Earth, exactly as designed. Before we go further, let me clear up something that trips a lot of people up. Telemetry, remote control, tracking. People use these interchangeably. They're not the same thing. Remote control is what you tell the machine. A burn command sent from Houston to Orion, fire the engine for 12 seconds. That's uplink. That's control. Tracking is where the machine is. Position, velocity, navigation, radar and ranging data, GPS on the ground, deep space network ranging in space. Telemetry is what's happening inside the machine. Temperature, pressure, system status, crew health. On Artemis II, all three were running simultaneously, every second. Control told the spacecraft what to do. Tracking told engineers where it was. Telemetry told them how it was doing. Remove any one of those three, and the mission fails. Here's something most people don't consider. Telemetry can go silent in ways you don't always expect. Some signal loss is planned. When Orion passed behind the moon on day 6, Mission Control knew exactly when the signal would go quiet, and exactly when it would come back. That 40-minute loss of signal was built into the mission timeline. Engineers simply waited. But on day 9, heading home, signal quality improving, Mission Control made a routine adjustment to the data rate on the return link. And the link dropped. Not a hardware failure, not a sensor problem. A routine communications adjustment during a data rate change that didn't go as expected. For a period of time, Mission Control had no telemetry from the spacecraft. It recovered quickly. The burn was executed successfully. But it's a real reminder, data loss doesn't always mean something broke. Sometimes it happens during transitions between normal operating modes. Good engineers design for these moments. They build in redundancy, they plan for signal loss, and they never fully trust any single reading without cross-checking. That's what makes telemetry reliable. That same discipline shows up everywhere, not just on rockets. Your car has an OBD port under the dash. Plug a scanner in and you're reading engine telemetry. The same concept NASA uses, scaled down. Your smartwatch is reporting biometric telemetry, heart rate, blood oxygen, steps, back to your phone. In the recent Miami Grand Prix, Formula One race, engineers on the pit wall are reading hundreds of data channels in real time from a car doing 200 miles an hour. Tire temperature, brake pressure, fuel load. They're making strategy decisions lap by lap, based on telemetry. And as machines get smarter, as we move toward autonomous vehicles, autonomous drones, more capable robots, telemetry becomes more critical, not less. An autonomous system is only as good as the information it has about itself and its environment. A self-driving car that loses sensor data doesn't know where the lane is. A Mars rover that can't report its wheel condition might drive into a rock it can't climb out of. Without the data stream, you're operating blind. So let me leave you with something practical. The next time you hear about a system, a spacecraft, a drone, a self-driving car, a medical device, Ask what telemetry is being captured and used for decision-making. Artemis II showed us exactly what that looks like. 9 days, 250,000 miles from home, thousands of data streams running continuously. Telemetry is the nervous system of modern machines. It doesn't make them smart on its own, but without it, engineers, operators, and computers are flying blind. And in space, that's not an option. I'm Alan from ARH Tech Lab. If this was useful, hit subscribe. Next time we're going deeper into how telemetry data actually gets processed, from raw numbers to the displays engineers rely on. I'll see you then.